Now let's study section 1.3, idealize the voltage and the current sources. Section 1.1.1 is ideal voltage source. An ideal voltage source is one that provides a given known voltage V, no matter what source of load it connected to, regardless of the current drawn from the ideal voltage source. It will always provide the same voltage. An ideal voltage source does not have to deliver a constant voltage. The quantity Vs can vary with time and still be ideal. Section 1.3.2, ideal current source. An ideal current source produces a given amount of current is no matter what load it sees. So from this graph, the current is constant. The current produced by an ideal current source does not depend on the voltage across the source. Section 1.4, electrical resistance. For an ideal resistance element, the current through it directly proportional to the voltage drop across it. The left graph shows an ideal resistor symbol, and the right graph shows the voltage-current relationship. The slope of the line is the value of resistance. Section 1.4.1, Ohm's law. Ohm's law says voltage is equal to resistance multiplied current. V is in volts, I is in amps, and the constant of proportionality is the resistance R. The unit of R is in ohms. Current is given in terms of voltage, and the proportionality constant is called conductance G, with units of Siemens. The relationships for power dissipated by the resistor can be derived using the following equation. The P, power, is equal to voltage multiplied current and is equal to I squared multiplied resistors. Is also equal to the V squared divided by the resistance. Section 1.4.2, resistors in series. If we have N resistors in series, the equivalent resistance is equal to Rs is equal to R1 plus R2 plus Q plus Rn. Let's see this graph. The graph A shows there are two resistors in series. It is equal to the resistance. The equivalent resistance is equal to R1 plus R2. Section 1.4.3, resistors in parallel. Equivalent resistance of resistors wired in parallel. As shown in graph A, there are two resistors that are in parallel. we can see that the voltage across the R1 and R2 are the same. Therefore, according to Kirchhoff current law, the equivalent current is equal to the current flow over the R1 plus the current flow over the R2. Therefore, the resistance in parallel, is equal to R1 multiply R2 divided by the sum of R1 plus R2. Or this also means the conductance of two resistances in parallel are equal to G1 plus G2. Section 1.4.4, the voltage divider. Let's first learn two-port networks. Two-port networks have a pair of inputs and a pair of outputs. A voltage divider is an example of two-port network. A voltage divider is composed by two resistors that are connected in series. VIN is the input voltage. The Vout is the output voltage. And this forms a voltage divider. A voltage divider is a deceptively simple but a surprisingly useful and important circuit. It is also the first example of two-port network. A voltage divider, if it is connected with an ideal voltage source, the Vout is equal to the VIN, the input of voltage, multiply the R2 divided by the sum of R1 plus R2, which means the voltage out is equal to the voltage over the resistance R2. Section 1.4.5, wire resistance. The resistance of wire depends primarily on its length, diameter, and the material of which is made. Rho is the resistivity of the material. Its units are ohms multiplied mils. L is the wire length. The unit of L is meter, m. And A is the wire cross-sectional area. The unit of area is square m. But the units often used in the United States are different from the standard units. The units expressed in the area is in circular mils. 1 circular mil is the area of a circle with a diameter equal to 0.001 inch. How can we determine the cross-sectional area of a wire in circular mils with a diameter d, also in mils? This is also the same question that about how many 1 mil diameter circles can fit into a circle of diameter d mils. The cross-sectional area of a wire with a diameter d is calculated using the following equation. the area A is equal to pi divided by 4 multiplied by square d square. The unit is a square mil divided by pi divided by 4 multiply square L. The unit is also the square mil per cmil. Therefore, A, the cross-sectional area, is equal to the d square. The unit of A is a cmil. Section 1.5, capacitance. Capacitance is a parameter in electrical circuits that describes the ability of a circuit component to store energy in an electrical field. If the surface area of the plates is large compared to their separation, the capacitance is given by C is equal to sigma multiply A divided by D. C is the capacitance. The unit of C is a farads. Epsilon is a permittivity. A is the area of one plate, square m, square meter, and D is the separation distance, m. The unit of D is a meter. A capacitor can consist of two parallel charged plates separated by a dielectric. Capacitance is equal to the amount of charge required to create a 1 volt potential difference between the plates. Since the current is the rate at which the charge is added to the plates, we can rearrange and then take the derivative to get current I is equal to dq divided by dt, which is equal to C multiplied dV divided by dt. Because according to the equation here, capacitance is equal to the Q divided by voltage. Therefore, the Q will be replaced as a C multiplied voltage. Capacitors in series and capacitors in parallel. The left side graph shows two capacitors in parallel. The equivalent capacitance is equal to C1 plus C2. The right graph shows the capacitance in series. The equivalent capacitance in series is equal to C1 multiplied C2 divided by the sum of C1 plus C2. An important characteristic of capacitors is their ability to store energy in the form of an electric field created between the plates. Since the power is the rate of change of energy, therefore energy is equal to the integral of power. So the energy WC, which is the energy stored between the capacitors, is equal to the integral of the power divided by multiplied dt. It's the integral of the voltage multiplied current, because power is equal to voltage multiplied current. And the current I, as we have learned, that is equal to C multiplied dV divided by dt. Therefore, the power, the energy stored between the capacitor is equal to C multiply the voltage integral. So the energy stored in the electric field of a capacitor is equal to the WC is equal to 1/2 of C multiply the square of voltage. Another property of capacitors is that the voltage across a capacitor cannot be changed instantaneously. To change voltage instantaneously, charge would have to move from one plate around the circuit and back to another plate in zero time, which in reality this won't happen. If the voltage can change instantaneously, therefore the dV divided dt will be infinite. This means the power could also be infinite, since power is the rate of the change energy. So in reality, we won't get infinite amount of power. Therefore, the voltage across a capacitor cannot be changed instantaneously. Now let's finish the section 1.5.